In this next set of examples, we're going to take a function and see if we can dissect it and write it as a composition of two or, in the last example, three functions. So we want to look at this here and say, can we think of this as a function inserted into another function or inputted into another function? And if there's always more than one way that we can do this. There's lots and lots of different answers, but I guess there's probably one choice that's more obvious, and this is a really basic problem here, so I think there's really only one choice that's obvious, and that is that we could think of this square root as the input into the function x plus 3. So, whoops, I got a bad pencil here. I'll switch to a pen. This might be a bad pen. I'm not lucky today. Okay. So this being our original, and then we're going to input the square root of x into it to get this final function cap f. So the way I asked you to do this, f and g, where g is the inner function. So we want the inner function, g at x, to be the square root of x. And that's getting inputted into this function, which is going to be the outer function, so we're going to call that little f at x, or lowercase f at x. And so that would satisfy what we're looking for. Again, you can be creative and come up with other answers. And then you can always use just x itself as your inner function, but that doesn't lead to any interesting results, because then your outer function is the original function. So don't use the function for the inner function, g at x equals x, the identity function, since then, let's put this in parentheses, the outer function is the original. Okay, so this process that we're doing is called decomposing functions. You take one function and decompose it into two or more functions. This will be important for those of you that are going to take calculus. For the rest of you, you know, you probably won't see it again, to be honest, but of course you need to do it here. But for those that are on the calculus track, you will need to be able to do this in calculus. So this is, you know, once you get some practice with it, it does become easier to see a function as a composition of two or more other functions. Okay, so on to the next one. Again, we don't want to pick just x for our inner. We want to pick something more interesting. So in this function, I think the choice is pretty obvious. You know, anytime you see an expression more than once in the function, that's going to be a good choice for you. So we're going to choose this for our inner, and then these will become our x's in our outer. So the inner is g at x is the linear function x minus 3, and then the outer, f at x, is 2x cubed minus 3x plus 1. So you'd have this going into both of those x's. And that's a good choice there. Again, you can come up with others if you get creative, but that is going to be the obvious choice, so we'll go with that. In the third example, we have we want to find three functions. So h being the innermost, and then g, and then f the outermost. So if we look at this, there's not too much going on here. You know, we could, if we were just doing this as two, let's do it two ways. So first, I'm changing the problem a little bit. F is f composed with g, and then we'll do this one for the second example. So we have, you know, three operations here. We've got absolute value, we've got subtraction of 2, and we've got the power. So if we took the, if we're only going to decompose it as two functions, I think there's two choices here. So let's do it one way, would be to take just this absolute value of x as our inner function, so g at x is the absolute value of x, then that means that f at x would have to be, so this is going to be our x minus 2 to the 1/2. A second way we could do this is a good one that makes sense to do two ways because we have two operations under a third. We could pick the absolute value of x minus 2 as our inner function. So absolute value of x minus 2, whoops, absolute value is there, sorry. That's why I don't like to use pens. And then the outer is going to be, this entire expression is going in place of x, so it's x to the 1/2. All right, so that's our first example, and then this is our second example. Okay. So because there are three operations, we can do this as a, composition of three functions. So the innermost is going to have to be this absolute value of x. And then that's going to get inputted into, I've got this such a mess here, let me rewrite it. Okay, so this is going to go into the next step, which is the subtraction of 2. That's going to be our g at x. So you basically work from the inside out. Now you're going to take this, and that's what's going to go in place of the x in the outside function, which will be x to the 1/2. I'm sorry, I don't know why I put absolute value of x here. This is not right. This should just be x minus 2. So that goes into here, and then let me show you. So h composed at g at x is h at g at x, which is, what is wrong with me? That should be g composed with h at x. G composed with h. Now you see why I don't use pens. I tend to make mistakes sometimes. Alright, so g at h at x, which is g at the absolute value of x. And so this goes into the x spot, and we get absolute value of x minus 2. And now this function, this result is going to go into f. So f composed with g composed with h at x. We're basically putting this result into f. So it's going to be f at, I'm running out of room, so I'm just going to put the function in. Absolute value of x minus 2. And so then you see we have the result we're looking for. Okay, you could probably see that without me showing it all to you, but I just wanted to show you the notation that we get the right function. So this goes into this, and then once that's in place of there, then that goes into there, and we're to the original function, the given function, I should say. All right, let's look at the last problem, and I'm going to sharpen my pencil here. So it's going to be loud for a second. Sorry, I don't have professional editing on my videos. I don't have time. Oh, my pencil sharpener's not working. I guess I'll have to stick with my pen. Alright, I'll try to do better on this one. Okay, so in this example, of course we have an application here. We have a store, Kohl's. We're talking about the different types of promotions that they run. So one is to run a percentage off sale, and another is to offer a dollar amount off your purchase. And that purchase, let's see, so we're going to suppose we have a coupon for 20% off, and then we also have a coupon for $10 off a purchase of $50 or more. And so Kohl's lets you double up on your coupons. You could use both of these, okay? So in part A it says, we're just going to assume we're going to use the one coupon. We're going to just use the percentage off coupon. Write a function for your cost after the discount if you spend X dollars. We're going to call this P at X. Okay, so of course if if you are getting 20% off, you're paying 80% of the price. So you can x minus 20% of x, or you can just write 0.8x. And so that's how, that's a better way to think about it. Then you don't have to do a percentage and subtract. You can just say, oh, well, if I get 20% off, I'm paying 80%. So our price is 80% of the original price. All right, in part B, you plan to spend more than $50, so then you can use your $10 off coupon. So if we assume we're not using the percentage off, what would this function be that represents the total cost after the $10 off? And that would simply just be x minus 10. You just take your $10 off the original price. Okay, so we have our two functions, and then in part C, we're going to use both coupons. So we're going to find P composed with T and T composed with P and interpret what each represents. So let's start with P composed with T. So this is P at T at X, which is P at X minus 10. So 0.8 times X minus 10. That replaced the X in the original function, right? So this X gets replaced with X minus 10. And that simplifies to 0.8x minus 0.8 times 10 is 8. So here's P composed with T at X. Okay, so what does that mean? So in this composition, what this means is they're taking the $10 off first. So say you spent $90, take out the $10, now you're down to $80. And now they're going to take the percentage off of that. Okay, and then let's compare what, so this is the $10 off taken before 20% off. Okay, and then in the reverse of that, T composed with P at X, we have T at P is 0.8x. Oops, I didn't put that's the T at P at X. I didn't write that down. But that you should understand that T at P at X, which is T at 0.8x. And so we plug that into T and we get 0.8x minus 10. So in this function, they take the 80% off first and then the $10 off of that, or excuse me, the 20% off first. So 20% off taken first, then a $10 discount. Okay, so if we're using both coupons, which of these would you prefer? So if you compare the functions, notice that this here is saying, okay, you're paying 80% of the original price, but in this one, after that discount, you only end up with $8 off. This one, you get a full $10 off of that, 80% of the original price. So we would prefer, I don't know which way they do it actually at Kohl's, but it would be better if you took the percent off first, or we prefer T composed with P because taking the, I already wrote the percentage off first, or off before the $10 discount results in, and notice it doesn't matter what the original price is, it's always going to be $2 extra that you save in $2 savings. Okay, so what's happening here basically is you're only getting, for the $10 off, you're only getting 80% of that $10 off. But if you take the discount, the percentage off first, you get the full $10 off. You don't have to have a discount off of your $10 off coupon. Okay, and then I should point out here, this would actually be a piecewise function if we did write our, excuse me, let me start over. I'm not making sense. In terms of like how much you actually are going to spend at Kohl's, if you went there for the day, you could only apply, you'd have to know which one of these they're actually going to do, and I don't know which one they're going to do. But say it's this one, and they actually do give you the percentage off first and then take the $10 off. So that gives you this discount, right? Then this one wouldn't even apply. So then what you would have is a piecewise function where your final price would equal just this if x is less than 50, but it would equal this if x is greater than or equal to 50. Because you can only use this minus 10 if you go over that $50 or equal to it, right? If you come to exactly $50, you'd be able to use this. So this would be an example of a piecewise function. Okay, one thing to think about in terms of shopping, if you ever notice, a lot of stores will say, okay, you get 40% off and then you get an extra 20% off, and a lot of people make the assumption that that means you get 60% off, but that's not actually true. Let me show you. This is kind of a little extra example. So suppose a store offers 40% off, then additional 20% off. What's the final discount? Okay, so a lot of people just assume that means, oh, you're getting 60% off. But the thing is, when stores do this, they're kind of sneaky about it. They're only giving you 40% off the original price, and then the 20% off comes off of the sale price, the price after this 40% discount. And so you're getting 20% off. So this is really, an inner and an outer part you're composing. 20% off the 40% off price. Okay, so what's the 40% off price? So you pay 60% of the original price X. Let's call it X. And so this is 0.6X. Right? Let's call that, well, we won't use function notation. Let's just say that's 0.6X. So that just bring this down. So you get 20% off this 0.6X, right? That's how much you would pay after the 40% discount. Well, 20% off the 0.6X, think of it as in terms, it's easier to do it in terms of how much you're going to pay. So you're going to pay, you pay 80% of 0.6X. So you pay 0.8 of his times, right, times 0.6X. Well, 0.8 times 0.6 is 0.48X. So interpret that. What does that mean? You pay your final, the final amount you pay is 48% of the original price. Okay, well, if you're paying 48%, then your discount is 52%. Okay, so not 60%. Actually quite a bit less than 60%, right? So be careful when you're shopping, that stores will do this to kind of trick people. what I always do when I'm in a store to make a, like a quick way to figure out how much you're actually getting off is to think, okay, I got these 2 discounts. What percentages am I paying of each? So in this case, it's the 60% and the 80%, and then just multiply those. 0.6 times 0.8 is 0.48. But remember, that's how much you're paying, and so your discount would be 100, or 1 minus that, or as a percentage 100 minus the 48%. That's the quick way to do it. Okay. Anyway, that was a little extra question. It's a good thing to know when you're shopping, that you're not getting as much off as you think you are.